All right, Kelsey, we're going to try this. Here's our picture. 55, excuse me, this right here is 35 degrees. This is 16 newtons. So that means we're trying to find what are we trying to find? We're trying to find the angular acceleration of this roller. And what that means is if you have something spinning, then we're trying to find the angular acceleration of this. We're trying to find out how much it's accelerating this roller as we push it along, the angular acceleration. So we're probably going to do that in radians because we're using a circle and we're using circular momentum, circular acceleration, that kind of thing. So, but what we've got to do is we've got to figure out what the force is that's being applied horizontally first. All right. Well, it tells us the force being applied at this angle here. So that means that we're going to use, instead of using 35 up here, we're going to use 55. And I think that was our first problem. So then when we punch that in, we're going to use 16 newtons times the cosine of 55. All right, 16 newtons times the cosine of 55. And when we do that, we wind up with 9.177, I think. All right. Now, those are important numbers because that tells us the force then that's being applied right here, 9.177 newtons. All right. Now, the thing we got to remember too is that newtons is a force, and force is mass times acceleration. Well, newtons is measured in the mass, and this mass is our unit is kilograms, and our acceleration is meters per second squared. All right. Well, if you'll remember, this thing gives us this radius right here of this circle. So now that we have a force being applied to this thing horizontally, we know how we've got to use the horizontal deal. I'm going to change this to red so we don't get our lines mixed up. But this thing's being pushed across the floor. So if it is, then we need to know it's. We're going to have to include its velocity and all of this kind of stuff. We're going to need to know. Obviously, it's not accelerating down, is what I'm trying to say. It's not moving down. It's moving across. That's why we had to figure out this horizontal piece. But it gives us this. I'm going to blow this circle up larger, and this thing tells us that this radius right here is 3.8 what centimeters. All right. Well, our normal forces are measured in meters, so this right here is going to have to be changed to centimeters. We need to make that note. All right, we're going to have to change that to centimeters. All right. Well, to do that, let's look at this force then. Is 9.177, and really we can only use two significant figures here, so really this is 9.2. You with me? 9.2 newtons, and our mass we know is 2.4 kilograms, right? We know that much. And therefore we can figure out the acceleration of this object is going to wind up being 3.8. All right, 3.8. But this is just going to be in meters per second squared is our acceleration because we haven't changed anything but we know we have to. All right, now to change this to meters, from meters per second squared to centimeters, we need to change it to 380 because there's 100 centimeters in a meter. So we've got to multiply this thing times 100, and when we do, we wind up with what? 380 centimeters per second squared is now our acceleration. All right, so we have 380 centimeters per second squared. That's how fast this thing is accelerating. That's how quickly it's accelerating as it's spinning along here. At 380 centimeters per second. It means it's speeding up 380 centimeters per second every second that we push it. And that's just because it's really not, the speed isn't changing so much as it's just changing direction, but we know that acceleration can be a change in what? Speed or direction. Remember that? All right, so because it's changing direction, because it's a circle. All right, but this is not an option in our answers. Our answers were measured in I believe they were measured in radians per second squared. And let me look at my little deal here. I'm looking on my phone right quick to pull that up. Well, I can pull it up right here. This will be pretty cool. I pull it up here, and you can see that it gives us radians per second squared. All right. So to go back over here, well, now we need to know what a radian is. A radian is, remember, this is the radius. Radian. radius, that's why we call it a radian. The radian is just another way to measure the acceleration of an object. It's another unit of measure, a radian is. It's not in terms of acceleration. We're going to use it in a second, but it's really just a unit of measure, just like this centimeter is. All right, but what this centimeter is telling me, let's look at what this circle is doing. This circle here is spinning 300, the wheel, the roller is spinning 380 centimeters per second every second. 380 centimeters, okay? That's pretty fast. Somebody's pushing that roller pretty quickly. Well, we can also say how fast it's spinning in relationship to this radius. And we know that this radius is only 3.8. And a radian, I'm going to change colors again. I'm going to change to green. If this right here is 3.8, then a radian is that angle of measure that is created when the distance traveled by a circular object is equals to the radius of its travel. Alright, so this side right here and this side right here are the same, are equal. Yes? And so when that happens, then we can draw a point from the center to this end point right here, and this is going to give us, that is a radian. That is 1 radian for this particular circle. Alright? This is the radian for this particular circle because this circle has a radius of 3.8. This is a radian right here. Whoop. Hang on, I got to answer my phone from my daughter. Hey, sweetheart, can I call you right back? All right, I'll call you right back. All right, bye. All right, so sorry about that. So what this is telling me then is that it wants to know this. The professor wants to know how many radians per second squared is this thing spinning. Well, all we have to do is set these things equal, and we'll see something. Since a radian here is 3.8 centimeters, and this thing is spinning at 380 centimeters. Now remember, since a radian, this particular radian for this problem is, or radius, is 3.8 centimeters, and this thing is traveling at 380 centimeters per second squared, then how many radians is it traveling? Well, all we got to do is divide 380 by 3.8 and we'll get 100. So this thing is traveling at 100 radians per second squared. And if I'm not mistaken, that would look like this problem right here. 1 times 10 to the second radians per second squared. All right? Now, I don't know if that's how you guys solved it, but that's kind of how I went through it.